This is a continuation of our review for exam 2. The practice problem that you see at the top of the page here is a really compact way of asking a question that we had on one of our quizzes and that I've emphasized quite a lot. And that is the way that a series is related to an integral. And this is what gave us the integral test, but more importantly, it also gave us the upper bounds on the errors when we're trying to approximate a series that can be compared to an integral. So if you remember, we drew two pictures where we had a function, a continuous function, and we had our values 1, 2, 3, 4, 5 across the bottom. These are supposed to be the same picture. In the one picture, we drew rectangles of width 1, where the left side of the rectangle hit the curve. And in the other picture, we drew rectangles of width 1, where the right side of the rectangles hit the curve. So this starts 1, 2, 3, 4, 1, 2, 3, 4. And these are supposed to actually touch the curve. So what these two pictures illustrate is the relationship between the sum of a series and the integral of a continuous function. We have set things up so the rectangles all have width 1, and the reason we did that is so that the height of the rectangle is actually numerically equal to the area of the rectangle. So when we sum the areas of the rectangles, we're really summing together the numbers that come from the heights of the rectangles. And we compare that to the integral. The integral would be all of the area under the smooth continuous curve. So in the picture on the left, the rectangles are winning. The rectangles are bigger than the blue shaded area. And in the picture on the left, the first rectangle's height is a sub 1. It's really f of 1. Right, we get that by plugging 1 into the function. That gives us the height over here above 1. I'll just mark it in yellow. So the height above 1. But we have set we'll have set the function up so that f of 1 is a1, and f of 2 is a2, and so on. So the first rectangle area is a1, the second rectangle area is a2, and so on. So the sum of the rectangle areas is just the sum, a1 plus a2 plus a3, and so on. And again, we can see that that is bigger than, and in general we'll say greater than or equal to, because we don't really know what that smooth curve looks like. So we'll hedge our bets, but we'll say greater than or equal to the value of the integral, and that integral, it starts at 1, goes to infinity, and is the integral of the continuous function. So the picture on the left illustrates that the sum of the a's, starting with a1, is bigger than or equal to the integral. The picture on the left, the integration sum is winning. The rectangles are smaller, but it's the same. The rectangles are formed the same way. So at first it seems like it doesn't make sense that the sum could be smaller here, but the reason that it's different is that this first rectangle that we're adding in here, that first rectangle, the height of it is the height of the curve above x equals 2. So the first rectangle here has area A2, the second one has area A3, and so on. So on the right-hand side, the sum of the areas of the rectangles is just A2 plus A3 plus so on. And so we'd write that the sum of the series starting with k equals 2. And from the picture, I can see that the sum of those rectangles is less than the blue shaded area, and the blue shaded area is going to be the integral from 1 to infinity of f of x, the continuous function. And so both of these inequalities are true as long as our picture looks like this, where the curve is decreasing the whole time. That's the reason that all of our left rectangles are too big and all of our right rectangles are too small, is because this function is actually decreasing the entire time. So everything we're saying here only applies once the AKs have started to decrease and never come up again. But once that happens, then this is true. And one thing that was really significant about this for our error bounds is that there's absolutely nothing special about starting this picture with x equals 1. If instead you went back and started this picture at 101 and 102, if that's what the picture looked like, then everything here would just get updated. Oops. Would just get updated accordingly. So you could go through and revise everything, and it would all be true for any starting point. And that's what gave us how we got error bounds in terms of intervals. Anyway, so that's what's really important. And if you go back and look at the old quiz on this unit, you'll see that this was actually the quiz question, was to tell me what this picture was showing you. The problem here is one out of the book that really compresses all of that information, but this is exactly what we need to answer it. So it's saying if you know the integral is a half, so in other words the blue area is a half, then what else do you know? Well, and we just have to do it as multiple choice because there's lots of stuff that we know. We just have to see which thing they're saying. So do we know the sum converges to a half? Well, no, this is the sum of the rectangles. So the sum of the rectangles would almost never be equal to the same thing as the integral. You'd have to really go out of your way to make that happen. So our pictures definitely don't look like our sum. The rectangles add up to exactly the same as the blue shaded area. So not A. The sum converges something less than a half. Well, this sum starts with k equals 1. So they're talking about this. This sum starting with k equals 1 is definitely bigger than the integral, so not less than a half. The sum starting with 1 would be greater than a half. And that's actually what C says. Right? So letter C is stating exactly what we're seeing in this picture. So for the exam, that's probably more compact than I would want you to do. I probably would rather do something more like the quiz question, where you can sketch this picture or explain to me why one of these inequalities is true. But that's what this question is based on.